Welcome to another episode of Systems Philosophy. I am going to build on the concepts we explored in episodes 1 and 2, the ship of Theseus, where we separated the persistence of a pattern from the persistence of the matter that makes up that pattern, and explored different ways in the idea space in which that pattern could be altered and in which our definitions of what makes up a thing start to become blurry. In episode 2, I took that further into the living cell and replication, asking the question, if we don't consider the original cell dies when it divides, then we could conceive of all living cells that surround us in the here and now as essentially being that original cell that we believe kicked off life on Earth around 3.5 billion years ago, or perhaps even longer ago if you believe in concepts like panspermia. A lot of this philosophy is about challenging framings or perception and trying to get you to see things from a different perspective, and using that perspective, explore the insights that that perspective provides. The living cell is a form that is a system that maintains its own structure. There was a physicist and thinker in the 1940s who developed the concept of a replicator that can contain the instructions and the machinery for its own replication. That abstraction is known as the von Neumann replicator. This way we can think abstractly in terms of mechanics we can imagine, of a machine that has instructions to maintain and repair itself, and also how to gather and structure the materials required to replicate itself. In science fiction, we could imagine our current situation where artificial intelligence takes over the mining and the factories, which then learn how to build all the components that make itself. And it could then replicate the structure autonomously on a lunar city or on Mars. The living cell is essentially an example of a von Neumann replicator. And von Neumann imagined computer punched tape as storing the information, because that was the information storage technology of the time. Today we could talk about hard drives or solid state drives or just memory. In biological terms, this is the DNA and the RNA and all the machinery of transcription. So the cell is a replicator that makes copies of itself and maintains its own structure by consuming energy from the environment. Thermodynamics tells us that doing any work creates entropy, and therefore my stand just about fell over. Um, the maintenance of form creates entropy in the greater environment, and it works just like a machine does, like a petrol engine or a battery. It converts energy into a form that can be used for the maintenance. From a systems dynamic perspective, proteins get transcribed from the DNA into RNA, ribonucleic acid, which then creates copies of useful proteins within the cytoplasm of the cell. And the structure of the proteins within the cytoplasm or the cell membrane is such that, provided the system keeps a certain level of coherence and has energy flows and persistence, it will continue to persist and run its operating program. And from that perspective, computer science and systems theory comes in very handy. The stable dynamic equilibrium has the ability to absorb damage and repair itself. There is, however, a tipping point, a cutoff, beyond which the system can no longer maintain coherence. So we talk about a coherent feedback loop system in the stable equilibrium and the possibility of losing coherence, so that the stability either dramatically collapses or slowly degrades. A living cell can absorb damage, it can survive certain degrees of environmental changes to which it internally adapts. That's the dynamic equilibrium. A change in the environment produces a change inside the cell. The system and the environment are dynamically coupled. This is another one of the fundamental principles that we will continue to explore. The fact that we can define the living cell as an entity, and yet that definition never separates the cell from its components or the cell from its environment. And yet the cell membrane is a real boundary that separates the cell's external environment from its internal environment and bounds the system's dynamics of its biology from the environmental dynamics and chemistry of the external world. So here we are starting to explore the boundaries between a system in dynamic equilibrium and the environment within which that equilibrium is expressed. And one of the attributes of such systems is that they are reflexively coupled. Reflexivity was a term first used by George Soros to describe the economy and the activity of economic actors within it. So if you are a sufficiently large actor within an economy, then your actions don't occur in isolation. They are reflexively coupled to the economy. And many traders, people trying to make a living by reading and interacting with the economy have found that. The same is true as a general principle for systems in dynamic equilibrium. Simple examples is that the living cell feeds from its environment. Therefore, by taking in food, it alters the environment. It might consume another cell, therefore altering the general population. It might consume chemicals, therefore altering the concentration. It also excretes into the environment. Therefore, the results of its metabolism alter the environment in which it then acts. This is a reflexive coupling dynamic, and it's important in terms of evolution itself. The classic evolution is that the biological organism adapts to its environment. The more nuanced view of evolution is the organism is a biological entity whose form is maintained in reflexive coupling with the environment. The form is in dynamic equilibrium, and as the environment acts on the organism acts on the environment. Within a petri dish, the bacterial colony grows and therefore changes the conditions for its own growth, with the relative position of the bacteria versus other bacteria starting to become significant in terms of nutrient gradients. It also consumes the nutrients and excretes waste products. That in turn changes the way that the internal chemistry of the bacteria work. And at a certain point, the food supply might run out and the bacteria will either start to die or enter a dormant phase. So the environment and the bacteria are always in interaction with each other. And therefore, when we look philosophically how we frame the system, we can look at the petri dish, we can look at the nutrient medium, or we can look at the bacterial colony or an individual bacteria within it. Each of those framings, paradigms or perspectives will give us a different view of what we are looking at. We can imagine that the bacteria just exists, feeding on the nutrient. In many physics examples, we take idealized cases, and so we ignore things that are difficult to calculate, like wind resistance and friction, when we do simple Newtonian mechanics calculations. Harmonics and vibration are another thing we tend to ignore. So we idealize the situation. That's part of how our minds work. Part of where I wanted to take this philosophical journey is from the concept of an object as an information field, and that field consists of relative positions and states of the atoms and chemicals within the object. So in the ship of Theseus, the object is inanimate, but the ship consists of an information field of relative positions of planks, timbers, like masts, ropes, sails, fittings, pulleys, all of which combine to make a ship. So the ship is both material and it is a design. This is a dualistic view of reality, not a materialistic view. The material composition of the ship is one thing, but it's important to take the relative design, what is in relation to what, because that describes what sort of object the atoms create. And then if we take the relative positions and we track those positions through time, then we get systems dynamics, how the design is maintained and degraded. This is entropy and repair, a dynamic coupling of a system in dynamic equilibrium. With the ship of Theseus, the original design helps maintain the equilibrium. So even if we choose to change the mast to a different timber, or the fibre used in the sail, or the design of a certain pulley, the ship remains the ship, and unless we wish to fully redesign it, the original dimensions and design will create a form of historical anchor. So the initial construct limits the scope of variability in the design, and it's the external maintenance by the shipwrights that maintains the design. In living systems, the design of the original cell and its dynamics that were able to sustain itself and begin reproduction set the boundary conditions, and from then on that original cell divided into daughter cells, and those daughter cells divided, and they were reflexively coupled to their environment. Those that maintained coherence lived, those that were unable to feed and repair their structure died. And that is essentially the dynamics of evolution. And over time, the dynamics of evolution caused the dynamic equilibrium in the cells to drift as different environmental conditions were tested against different cells. The cells themselves reflexively coupled with the environment, changing the chemistry of Earth's atmosphere, of Earth's rocks and minerals. Limestone is wholly biologically constructed. Oxygen in the atmosphere is biologically created. The reflexive coupling of the living system and the environment changes both over time. So the dynamic equilibrium drifts, and we get the dynamics of evolution, where cells differentiate into different varieties, different lineages, and ultimately different species, although with microbiology of the individual cell. The promiscuity of genetic interchange makes it so that cells can pick up and deposit rings of genetic code into their environment, and therefore share information about what works and adapt on the fly. But that is a detail that we'll perhaps explore another day. For the moment, I've started to build on the concept of dynamic equilibrium and how it can evolve, how it's reflexively coupled, and how a perturbance can result in that equilibrium being destroyed. Now, when a cell no longer lives or can no longer sustain its form, it doesn't just go back to all the components that it ate. What it does is it gives its form to the environment, So all the components that made up that living cell are now reflexively coupled and available for other living cells. So its last act is to modify its environment with its own corpse. And just to take it back to something more simple, if we have a candle flame and we bring a second candle to that flame, we then separate the candles and we have two flames. The flame itself is a combustion process. The combustion process is stable once started, so it's in dynamic equilibrium. However, it will not spontaneously start on a fresh candle wick, and therefore the flame needs to be passed from wick to wick. And so we can use a flame to light a flame. The flame's dynamic equilibrium can also be blown out, like a candle in the wind, which is the metaphor for life and why fire has so often been associated with life, because the dynamic equilibrium of the flame and the dynamic equilibrium of the cell have a lot in common. I think that's where I'll leave it for here and now, today. I'm still early on my journey of creating this content, and today I'm experimenting with different settings. The setting today is the Tasman Sea, the Southern Ocean, near the town of St Helens in northeast Tasmania.